This problem is a dependent motion problem. That's because when you pull on this rope, B is going to move, so the motion of A will control the motion of B. They're dependent on each other. All right, so if the end of rope A is pulled down at a speed of 1 meter per second, determine the speed at which block B rises. All right, so we have the speed of A is 1 meter per second, and of course, because this is a dependent motion problem, when you move A, B will move. Now, a lot of these pulley systems, you can determine the answer through inspection, counting the ropes, counting the pulleys. But we want to develop a technique that will not only solve simple problems, but more complex problems. All right, so what we're going to do is first identify a datum. Now, datum is something that's fixed that we can measure the moving particles from. And then we're going to measure the position of every moving particle relative to that datum. Once we have those positions, we can get the rope lengths in terms of those positions. This is called the position coordinate equation. And then we can take the derivative of that position coordinate equation and determine the relationship between the velocity. All right, so the first thing is we want to draw a figure and label the datum and measure the positions. So in this instance, I've chosen this top fixed pulley to be our datum. It does not move. And then I'm going to measure the position of every moving particle. So A moves, so I'll measure to it. B moves, so I'll measure to it. Now notice that I measured to the pulley and not to the block. It really doesn't matter which one you measure to, they move as one. But conceptually, it's better if you measure to the pulley. All right, and C moves, so I'll measure to that. All right. The next thing we want to do is relate the rope lengths to the positions. So I've labeled the ropes as rope 1 and rope 2. All right, so rope 1, how long is it? Well, it's 1 SC plus 1 SB. And then the little parts that go over the pulley, that's part of the constant. That never changes. That distance never changes. So that's in the constant. All right, rope 2. Okay, so what is rope 2? Well, it's this little length, which is SA minus SC. Then this length, which is SB minus SC. And then we have an SB. So that's what we have, the 3 lengths. And then we have the parts that are going over the pulley and such, which are constants. All right, so next we can take the derivative of the position coordinate equation. Now the length of the rope doesn't change with time, so that means the derivative is 0. And then we just take the derivative of each of the positions. So we can see from rope 1 that we can relate the velocity of B with the velocity of C. And then we can use that information and plug it into rope 2 equation to find out what's the relationship between A and B. All right, so I've just repeated those equations here, and I'm going to take the relationship between B and C, plug it in here, and so we get rid of that C and find out that the relationship between the speed of A and B is -4. So if we know the speed of A, then we know the speed of B, which is -0.25. Now what does the minus mean? Well, we're measuring everything from the datum away. So everything that's moving away from the datum is positive. Everything that's moving towards the datum is negative. So B is moving towards the datum, which makes sense. You pull down on A, B moves up. So that's why you get the negative. And I've just replaced that negative with an arrow indicating that B is going up.